Okay, mass spec. Then we'll move on to substitution. And quiz, likely on Monday.
The next time.
Okay guys, good morning. Happy Friday. We got a handout. I'll divide it into 2 stacks. Please take one. This is the handout on elimination chemistry. Elimination comes after substitution. Let's continue with mass spec. Lab will meet downstairs this afternoon. Any questions about anything? Any questions?
Dr. Stevens, did you decide when those lab reports will be due?
Lab report, shaken not stirred, will be due Monday week.
Okay.
Monday, this coming Monday is your group lab. Following Monday is the individual shaken not stirred lab report.
I do have a question about the group lab report. So I pulled up a journal from the publication you suggested, and it put the author emails at the back of the paper. Would you like that, or would you like it up at the top where we put our contribution?
Unless it specifies, it's up to you.
It's up to us.
You're driving the boat.
Do we need, like, literature sources for the safety data, or just for the physical properties?
Just for the boiling point of your product. Literature boiling point. Anything else can come from generic websites. Other questions? Okay, guys, mass spec, where we left off at. What's the name of these ions that are formed from carbonyl compounds in mass spec? Like the carbonyl cation. Name of this? Acylium ions. Yes, you'll actually form acylium ions in organic tube. In reaction mechanisms. Here we're forming it in mass spec. 2 different acylium ions possible up here, depending on cleavage on either side. Resonance stabilized. Actually, the resonance structure, okay, you got the resonance structure drawn. Which of the 2 is major? Triple bonded, right? More bonds, even though the positive is on oxygen. Acyliums, Nucleophilic, you need to know, and including your group report. Compound down here, both of these compounds have the same formula and molecular weight. They're both isomers, constitutional isomers. Down here though, no matter which side you cleave, if you cleave over here or here, you're going to get the same cation. Either way, loss of 29. 86 minus 29 should be 57. Hopefully that's 57. Ends up being your base peak. What is this? Is this 86? Probably 86. There's your molecular ion.
Oh no.
I don't know why that happened. That's the good news that I can get them closed and you can't get that stuff out.
Oh, wait,
I did get it on my clothes?
Yeah.
Better not. I might get into something I don't want to get into. Maybe I just had my hand on there and it drained it out. I don't know. Okay, either side you cleave. There we go. Nucleophilic not possible. If you look up nucleophilic, it actually requires a gamma hydrogen, alpha, beta, gamma. Okay? First carbon coming off of your carbonyl, that's called alpha. Beta. There's no gamma. Unless there's no gamma hydrogen, you can't do a McClafferty here. Pretty straightforward. Essentially, if you had those two compounds and you're asked to match them up to these two mass specs, could you do it? Well, you would say, okay, what do I expect here? I expect a cleave here to give this. It has a certain mass. I expect a cleave here to give that. It has a certain mass. And then I would look for which one contains those masses. Acylium ion. Okay, over here is a little practice for you, if you haven't done it already. Here are three spectra, spectrums. Spectra. Here are three compounds. Match compound to spectra. Please be doing that, and we can look at it at another time. We'll see how you did. The remainder, probably, well, let's go ahead and do it real quick. It's a little bit of miscellaneous, but the miscellaneous stuff is important. This just shows you, we talked a little bit about GC mass spec in lab. Okay, you're dealing with a GC mass spec right now for your group lab. This is a GC mass spec of a reaction product where we attempted fluorination. This was actually the starting material. We tried to fluorinate the ring. This was the product mixture, probably after an extraction, and it showed this. Let's get rid of that. Was the reaction successful? What do we now have in the reaction mixture? GC showed 1, 2, 3, 4 main components, with one being major, and it gets less, and that's kind of much, very minor trace amount. We can get mass spec of each component. Below are the mass specs, 3 of the 3 main things. Retention time coming off the column of about 3.6. Now it doesn't list the retention time here, but this mass spec came from 3.6. And so we just said that's A and this is A. That's how we got that. And then at 4.7, it gave this mass spec. Okay, basically these are the 3 mass specs for those 3 peaks. What we found is the biggest peak, which was C, actually has a molecular weight of 237. No, is it 237? Not sure what that is. Looks like a molecular ion of 237. 237 ends up being the starting material, where it did not react. But we also had mass specs that showed 255. 255. And we also had a compound that showed 293. And 293, if you think about it, is where the compound has 3 fluorines. And so this was good evidence that not only did we monofluorinate, but we also trifluorinated. Now, we really didn't have to interpret any cleavages, because here we could just look for the mass, the original mass, the molecular ions. That was the reagent, the reaction. And this reaction gives 3 main products: mono and trifluorinated. I don't think we ever figured out what that was. It was pretty minor anyway. One of the problems with these reactions is they just won't go to completion. Even if you use excess fluorinated reagent, the starting material just remains in your reaction. It won't all react for some reason. But that was using GC mass spec. Obviously, the mixture is not pure. Well, any mixture is not pure, right? Mixture is a mixture. It looks like 4 components there. What does a pure GC look like? Well, over here, here's a nice pure compound. GC is one nice peak. Okay. This is what you want for a pure compound. Molecular weight 337, and I believe it shows 337 down there. That's a compound made in the Organic 2 lab here, if you have me. Okay. Now, if you start dealing with GC on your own, you'll have the GC parameters. Okay. You can just look at this. Typically, you set your temperature, flow rate, etc. All this can be set. It's a little more involved than just running an IR. IR compound hit start, right? It's all there. GC, a little bit more. Let me make a comment about high resolution mass spec. Everything we've been doing is low res, whole numbers. Okay? You can do high resolution mass spec, which typically gives you 4 decimal places. We mentioned last time that's also more money, right? More expensive instrument. Look at this example though. All 3 compounds here have a nominal mass that is a whole number mass of 84. So if you were just looking for a molecular ion on a low res, it'd also say 84. But if you do high resolution mass spec and get 4 decimal places, now you can see a difference in these. Read through there. It's a series of questions, but it's meant to illustrate what high resolution mass spec is about. Okay. We do not have a high res instrument here. And on the back, that's a little application of direct analysis. Typically, when you do a mass spec, you first dissolve it in a solvent to make a solution. But more and more lately, folks are developing methods for doing direct analysis, and that's what it's talking about on the back a little bit. Okay, in the end, there is that one where we need to assign the 3 compounds to the 3 different spectra. We'll look at that next time. Let's get back to substitution. Everybody get a yellow handout? Okay, substitution. Seems like we left off with making oxygen a better leaving group. Oxygen is not a good leaving group for either one of these mechanisms, SN1 or SN2. Typically, you need to make a positive oxygen. You do that by protonating it with strong acid. Then it will become a leaving group for either mechanism. Not only OH can be a leaving group, any oxygen can. We can also just have OR groups, like O-methyl, O-butyl, or whatnot. Okay? If we react this with HBr, let's see what type of products we have. I think the products are going to be phenol plus ethyl bromide, or 1-bromoethane. How do we do? Phenol plus bromoethane. How do we do? Everybody got it right?
Oh, I'm getting there.
Good. All right. No need to discuss it, right? Everybody got it right. Great. Good job. Let's move on to the next one then. By converting OH to a tosylate, what's another way to make oxygen a good leaving group? By converting the OH to a tosylate. Okay? What's a tosylate? Guys, I know more than about 10% didn't get that previous one right, but nobody says anything. I've seen answers written and they were not right. They were willing to just move on and not discuss. That's a very fundamental mechanism there.
Will you go over it, please?
Maybe next time. All right, guys. How do you make OH a better leaving group? You make it positive oxygen. Another way to do it is to convert it to a tosylate or mesylate triflate. Tosylate. This is a tosylate. Tosylate stands for toluene. A benzene with a methyl, that's toluene. You'll learn that in Organic 2. Sulfone, so it's like, or sulfonyl, toluene sulfonylate. It's shortened for that. Called a tosylate. It's abbreviated OTOS, although that's my abbreviation. Most people, formerly it's OTS. But I do it OTOS. All right? Now, this used to be an OH. Basically, we're putting this on the oxygen instead of, okay, this is called a tosylate. The tosylate will serve as a leaving group. This oxygen will serve as a leaving group, nucleophile. We can attack the carbon, kick off that oxygen without having to protonate it. You don't have to protonate this oxygen. It will leave on its own, just like a bromine or iodine will. It's actually almost better than a bromine iodine. Why? What does this give? Well, it gives your product nucleophile, right? What's the leaving group look like? Okay. What is the oxygen becomes what? Third lone pair. That's a minus. Okay. That's phi-phi-pho. That's Greek for phi. That's Greek for, basically, that's abbreviation for an aromatic ring. Okay. But here's your structure. You're asked to show tosylate. That's a tosylate. But that's just abbreviation for an aromatic ring. This here. If this was OH, we would have hydroxide as leaving group. This is a much better leaving group. This will not leave. Why is this better? It must be more stable, right? Why is it more stable? Resonance. The anion is resonance delocalized. Is this anion exactly on oxygen? This oxygen? Anion's on the other oxygen. What about here? Is some of the anion here? Yes. Resonance stabilized. Okay, it's a resonance stabilized anion. It's more stable. It's actually more willing to leave. You do not have to protonate this oxygen. This would not be resonance stabilized. That's a tosylate. We'll see how to make tosylates below. You can also have variations of this. If this is a methyl out here instead of a toluene ring, it's called a mesylate. If it's a trifluoromethyl, it's called a triflate. And that's actually the best one. Because not only is this anion stabilized by resonance, but if you have a CF3 group here, you also have inductive withdrawal. A lot of inductive. At the introductory level, you'll only see tosylate. But mesylate was shown on the very first page of the handout. The drug synthesis, they used a mesylate instead. How do you make these? You make them from the OH group. We can make this a better leaving group by protonating it with strong acid, or we can convert it to a tosylate. This is a synthesis, and you actually isolate this. Okay, you make your tosylate, you purify it, you recrystallize it, however. Then you can move on and react this with a nucleophile. Okay. How do you make this? You make these from tosyl chloride. That would be a chlorine with the tosyl. Okay. Tosyl chloride. And let's see. I'm not going to do this mechanism because it's not a straight substitution, or it's not a substitution SN1 or SN2. But essentially the oxygen is bonding to the sulfur and replacing the chlorine. The oxygen is now on the sulfur instead of the chlorine. So it's a substitution. We make this plus what? If we just balance it out, oxygen is now bonded here. What else did we generate? Chlorine. Chloride plus what else? Where's this H at? It's gone. HCl plus HCl. Pyridine is a base. Pyridine, I don't know if we've seen it before. Benzene ring with one nitrogen, it's a base. Pyridine is there to consume the HCl. We will not look at this mechanism. It is a substitution reaction, but it's not SN1 or SN2. Okay? Once you get your tosylate made, then you bring in your nucleophile and you can kick off the tosylate. LG. LG, right? Kick it off. Of course, if you're doing SN2, you're going to get inversion, and now it would be inverted. Note that you would not get any inversion here, because the oxygen reacting, why would it invert here? Okay? There's no chemistry at the carbon when you make your tosylate. So there's no change here. But when you do your substitution, now you have chemistry at the carbon, backside attack, kick off the leaving group, and now you have inversion, SN2 inversion. Okay, two ways to make oxygen a better leaving group. Protonate it with strong acid or convert it to a tosylate. What about other atoms on the periodic table? Halides, oxygen. What about nitrogen? Can nitrogen be a leaving group for SN1, SN2? Yes, it can. But as with oxygen, typically can only be a good leaving group if you give it a positive charge. Now, it's kind of rare to see nitrogen as a leaving group. Oxygen all the time. Actually doing it in the lab this week. Nitrogen more rare. But if we can make it positive, again, it can possibly leave. Let's look at this interesting reaction. Herzig-Meyer reaction. Okay. You thought these guys used to just sell furniture, but they also do chemistry. Herzig-Meyer? Is that right?
I guess you have to be over 30 to get that.
Okay. This is a dealkylation of a tertiary amine. It's a tertiary amine. It's an aniline with HI. What does dealkylation mean? Removing an alkyl group. Okay? Two alkyl groups on the nitrogen. Now only one. HI. We can show this ionic. Well, nitrogen tends to be a base. We can protonate it, yeah? I'm going to draw these methyls as CH3s. So we know how to protonate an oxygen or a nitrogen. How do you get final products from here? Should be pretty intuitive. What's going on? Finish up the mechanism.
I takes the.
It could supplemental, then
Finish up the mechanism. Anybody got it? Anybody got something?
Is because the methyl is partial positive because of the nitrogen, does it easily graft from that iodide? Is that what's happening? It's really like
Anybody have it?
and then it's actually grabbing it, isn't it? See right here?
Anybody else? You know there's a lone pair there, right?
Mm-hmm.
Right?
That's what grabs the hydrogen.
no, it does.
Huh?
Right, and there's a lone pair there, right?
Yep. And that's what grabs the hydrogen.
Your arrow movement does not leave a lone pair there. It leaves that nitrogen with no lone pair, right? No, I was talking. H plus doesn't have any electrons. Arrows show movement of electrons. H plus doesn't have any electrons, so you will never have an arrow coming from H plus. Here's your nucleophile. We attack the carbon and kick off the leaving group. What does that arrow movement give? I is now bonded to methyl. I mean, this is a CH3I, right? And what does this arrow mean? This moves on to nitrogen as
That's a lone pair.
lone pair. I mean, it's got a lone pair, right? I mean, just because it's not shown doesn't mean it's not there. If it didn't have a lone pair, it would have a 2+ charge.
I didn't know the I. Saying any I. I didn't know it was the I.
You didn't know I?
And I didn't realize that was an I. It looked like an L. Male. That's why I was like, maybe it's like short.
All right, well, what do you think that was?
That's an I because it's the HI. I mean.
Okay, that's methyl iodide.
Got you. Okay, well,
I
that
got
makes sense. Yeah.
We have, what are we doing here, guys? We have nucleophiles. We have nucleophiles attacking carbons and kicking off leaving groups. That's what we've been doing this whole handout. Nucleophile attacking carbon, kicking off the leaving group. Can nitrogen be a good leaving group? Yes, if you make it positive. We made it positive by protonating it. Nucleophile, kick off the leaving group. Okay? Overall, though, we have removed a methyl group from the nitrogen. That's a dealkylation reaction. It's kind of unique. It's called a Herzig-Meyer reaction. What about sulfur? Can sulfur be a good leaving group? Yes, but as with oxygen and nitrogen, typically you got to make it positive first before it will leave. Your body uses sulfur a good bit as both nucleophiles and as electrophiles. Okay? When your body makes norepinephrine, I'm sorry, not epinephrine. Epinephrine. We call it epinephrine. What do they call it in England? Yes? Huh? What? Very good. Adrenaline, yes. Make adrenaline from noradrenaline. Okay? What's the difference between norepinephrine and epinephrine? The nitrogen has a methyl group on it. Okay? How is this made in the body? Right now. You guys have made this in your body sitting here in the chair.
It's in your pituitary gland.
It's made using this biological molecule called SAM, S-adenosine methionine, I believe, or something like that. But it's got a sulfur, positive sulfur with a methyl group. This nitrogen is a decent nucleophile. These electrons will attack this carbon and kick off the positive sulfur in an SN2. Okay? Positive sulfur serving as a leaving group for this chemistry. Okay? The nitrogen has to lose a proton to go neutral. You can do that. Something can take a proton to go neutral. We've taken protons to go neutral when we did alkene chemistry. You know, water can take the proton, the acidic proton at that point. But this guy serves as a methylating reagent in your body. Okay? You can also buy this stuff at like the health food store if you need more methylating agent. You can take it as a supplement. Okay? So this is an example of sulfur. By the way, what does nor mean? Nor means like no. It's no, nor. Like Norway, no way. Like stay away. Don't come this way. Norway. Norepinephrine. It basically means something's been removed. If you have epinephrine and you remove a methyl, you get norepinephrine. That's a common terminology. Very often when you see nor, that means something has been removed from that. Okay?
It's interesting because they both have two very different reactions in the body. It causes two different, just that one methyl makes the difference.
Yeah, just like amphetamine and methamphetamine.
True.
Methamphetamine has a methyl. Yep. That's why it's called methamphetamine. We'll learn how to make meth in organic too. Usually. Okay, application time. Right? Remember watching Sesame Street? They always have application time? Okay, time for application time. Nitrogen, sulfur, leaving groups, and mustard type alkylating agents. Okay? This is called a sulfur mustard gas. Okay, it looks like a very small molecule, yes? Very bad stuff. Bad stuff. Used as a chemical warfare agent in World War I. All right? Very reactive. You get it in your lungs, it's going to react with everything. The eyes, everything. Reacts because it's very electrophilic. It does substitution reactions. Why is it so reactive? By the way, we said that something like this, you know, like ethyl chloride, this is not that reactive. We spray it on baseball players to numb the ankles. We wouldn't spray some deadly toxic gas in the baseball stadium. It's very similar. What's the difference? The difference is the sulfur here. What happens is these electrons sitting right there, boom, and kick that chlorine off. And it forms this three-membered ring. At this point, this is very electrophilic. Because now the sulfur is positive. And the sulfur positive will serve as a leaving group. Not only that, it's a strained ring. So it wants to be opened back up. So if you have nucleophiles around, like in your biomolecules in your liver or lungs or eyes or anywhere, and most of them have like nucleophilic amino groups, it's going to come in here, attack the carbon, and kick off the positive sulfur. So it self-generates a very reactive species. You don't need strong acid to make the sulfur positive. It's self-generated. And you can't keep that from happening. Very reactive stuff. You're gonna, okay? Now your nitrogen is bonded to an alkyl group. We have alkylated our DNA. Doesn't sound good. Sounds like cancer causing. Alkylating agents. Okay? Bad stuff. Now, some of these things, you also have nitrogen mustards. By the way, it's called a mustard because this is kind of yellow. The term mustard is now sort of generic. I don't think this compound's yellow, but it's called a mustard because the chemistry is similar. We've got this nitrogen here. It will come in here and self-generate a very similar thing. Becomes very reactive towards nucleophiles. This is actually a drug used to treat leukemia. Because once you get the self-generated three-membered ring, it typically will selectively react with cancer cells. Okay? Why? Well, that's a deeper discussion about why it's selective. Actually, it's not that selective. But it's selective enough to work and not completely kill the patient. But we know sometimes that cancer treatments can be very harmful. I don't think it's that selective, but it's selective enough to have some benefit. So, this is the idea of sulfur or nitrogen mustards generating. It's very electrophilic. Hopefully that makes a little sense up there. Okay, in the past, above, we've been looking at the leaving group. And we also looked at the carbon that's being attacked, like substitution. For example, SN2 mainly for primary carbons. Tertiary carbons, you don't want to do SN2. Leaving groups. What about the other component, the nucleophile component? Let's look at that component. And right now we are focusing on SN2. A lot of this applies to SN1, but when we get through, we'll sort of focus a little bit on SN1. What about nucleophiles? First, we can say that anions are more nucleophilic than the neutral counterpart. Which is more nucleophilic? They both have long pairs, but hydroxide is more nucleophilic. It's a better nucleophile. It's going to be more attracted to a partial positive or okay? Hopefully that makes sense. Now, nucleophile, what's the difference between a nucleophile and a base? For example, which is a better base? Hydroxide. What's the difference between nucleophile and base? All right, if this attacks here, kicks that off, we call it a nucleophile. If this attacks here, we call it a base. The only difference is it's a base when it attacks an acid, a proton. If it attacks something else, it's called a nucleophile. Now, the stronger base. Usually, base strength correlates with nucleophile strength, but not always, and we'll state some exceptions. Well, there are some things which are good bases, but poor nucleophiles. All right? What's a stronger nucleophile? Well, this one, right? I mean, according to the statement here, the anion is stronger than the neutral. Does that mean that the neutrals are not nucleophiles? They can be nucleophiles. They're just weaker. Now ultimately we'll define what is a strong nucleophile. And actually ammonia will be defined as a strong nucleophile. Just like we defined it as a strong base. What were strong bases?
SP3.
Anions or
SP3.
sp3 nitrogens? sp3 nitrogen. That's a strong base and nucleophile. It's strong. But guess what? It ain't as strong as that. Because that's an anion. Okay, number 2. A less electronegative atom has a more nucleophilic lone pair. Again, a lot of this goes hand in hand with base strength. Which is a stronger base, ammonia or water? They're both neutral. Ammonia is a stronger base. We defined it as a strong base. Which is a better nucleophile? They're both neutral. Yes, ammonia. Because a less electronegative atom has the more reactive lone pair. Nitrogen is less electronegative. Oxygen holds the lone pairs tighter. It's the same as when we discussed base strength. So that's an example in the same row. What about the same group? Which is a stronger nucleophile, H2S or H2O? H2S is a stronger nucleophile.
Because of the atomic radius?
Because what?
The atomic radius?
That helps. I was going to say that the sulfur is just a worse parent. Oxygen holds the lone pairs tighter. Okay? Right? The lone pair is held tighter to the oxygen, it's not going to want to go attack this. Oxygen is greedy, holding the lone pair density tighter. Okay? The size also helps. Well, the size kind of goes hand in hand with the electronegativity. But size also helps. I don't think I want to get into it. We've explained it enough. In the end, neutral sulfur compounds tend to be good nucleophiles. And your body uses sulfur as a nucleophile a good bit. Which is a better nucleophile, I minus or F minus? This is where we have a little bit difference between nucleophile and base. Iodine is a better nucleophile because it's less electronegative. Which one's a better base though? F minus is actually a better base. Which is more stable, I minus or F minus? I minus is more stable. That's why F minus is a stronger base. If it's more stable, how could it be more nucleophilic? Why is it more eager to go attack? It's a little counterintuitive.
Because those electrons are further out.
Electrons are further out, they're not held as tight. And so it's more willing to attack the carbon. But it's not more willing to attack an H+. Okay, it's counterintuitive there. It's contradictory.
I have a question. What if we're comparing Cl
Cl minus and oxygen minus,
this oxygen is OH?
OH minus, which is a stronger nucleophile.
Would be OH minus because maybe so.
Well, based on what's written, less electronegative atom. Which one's less electronegative? first off, we're not going across the same row, and we're not coming down the same group. We're going diagonal. We're doing apples to oranges, which is also more difficult. Okay? More electronegative, they actually may be pretty similar, but the halides are, in practice, more electronegative. Which is a better base? Clearly hydroxide. I would say this is more nucleophilic. You also have other things that come into play. I'm typically talking about in solution. Books will take you into the gas phase, and they will tell you how in the gas phase sometimes things can be different. I would say hydroxide is a better nucleophile. I wouldn't ask you that question. It's apples oranges. But on the other hand, what about I minus versus that? See, I would now say I minus is a better nucleophile than that. Even though that's a stronger base. It's not counterintuitive. I wouldn't expect you to know that. What I do expect you to know is I minus is a great leaving group and a great nucleophile. But you got apples and oranges. And that's tough. It's tough for you guys. Don't go tell anybody else it's tough. So for a knowledgeable chemist, it should not be tough, but at the introductory level, apples and oranges, it's tough for you guys, right? Yes, it should. Because I really, these statements are not meant to be tough. They're meant to be, but these statements only apply here or here. Okay. All right. We talked about steric effects of the thing with the leaving group, right? I mean, you got this, pretty good for SN2. We start doing this, no good for SN2, right? We have trip to the dentist. Sterics hurts, substitution, SN2. What about the nucleophile, though, the thing that attacks this? Well, sterics also hurts that. Nucleophiles, all right? Let's go back to just some good, nice little substrate here for SN2. Which one of these three is going to attack this easier and thus faster? The primary amine. Okay? Bam. SN2. Faster. That's faster than this, and this is faster than this. Because once you become tertiary amine, okay, you don't really need to be drawing all this here. I'm going to draw it quick. The idea is there. Okay, if you got a tertiary amine, right, these things are getting in the way of this approaching here. You know, because this, I got it drawn that way, but it may just rotate and be down like this, right? I mean, how is this going to get in here? It's got all this, okay? So it just makes sense. Substitution here, bad. Substitution here, also bad. Okay? Actually, tertiary amines, such as triethylamine, is considered non-nucleophilic. It's too sterically hindered. But it will still act as a base. Because when you attack protons, H+, okay, there's really no steric hindrance there because this is so small. And it's spherical, so you attack it from any direction. So acid-base reactions aren't influenced by sterics. They aren't hindered by sterics. But SN2 is very much hindered by sterics. So this is a non-nucleophilic base. It won't typically act as a nucleophile. And that can be applied to any nucleophiles there. I just showed you a series of amines. For example, we can come down here and look at oxygen nucleophiles. All right? Now here, the substitution is not on the oxygen. There's only one carbon on each oxygen. The substitution is next door. But even though it's next door, it still makes that congested. Okay? That is, if I walk right through here, I can go right down the aisle. But let's start putting lots of groups on here. And then, uh-oh, I just knocked some people in the head. I got all these ethyl groups. And so I'm like, hold on, I can't attack. But instead, what if I was primary? Boom, backside attack. Bam.